For the entire history of human civilization, our solar system has been keeping a secret. There are 8 planets. You learned that in school, and 9 if you grew up before 2006. Then back to 8 after Pluto got demoted. And every textbook ever printed has assumed that was the whole list. A research team at Princeton just put out a paper that says we missed one. Not Planet 9, that one we have been hunting for almost a decade and still cannot find. Something else, something closer, something that, by the rules of how planets are supposed to form, has no business existing where the math says it does. They are calling it Planet Y. And the only reason we are even hearing about it now is that a 15-degree warp in the outer solar system finally gave it away. Stay with me, because what they think is hiding out there is stranger than anyone wants to admit. A research team at Princeton University has just put forward a new candidate for a previously unknown major planet inside our own solar system. They are calling it Planet Y. The candidate is a rocky terrestrial body somewhere between the mass of Mercury and the mass of Earth, orbiting between roughly 80 and 200 astronomical units from the Sun. That puts it in the same general region of space the Voyager 1 spacecraft is currently transmitting from, after almost 50 years of continuous outbound travel. If the inference holds, this would be the 9th major planet of our solar system. And it would be, by current planet formation theory, a body that should not be able to exist at that distance. I want to be clear with you right at the top, because this story is going to get pulled in 2 directions the moment you start reading about it elsewhere. Planet Y is not Planet 9. Planet 9 is the longer-standing hypothesis put forward by Mike Brown and Konstantin Batygin at Caltech back in 2016 for a Neptune-class body of 5 to 10 Earth masses, orbiting 400 to 800 astronomical units from the Sun. We have been hunting for Planet 9 for almost a decade now without success. Planet Y is something different. It is closer, it is smaller, it is rocky, not gaseous, and it is the answer to a different anomaly entirely. Here is what Princeton has actually found. Out beyond Neptune, in the deep Kuiper belt between roughly 80 and 200 astronomical units from the Sun, there is a population of icy bodies whose orbits are tilted. Specifically, they are tilted at about 15 degrees relative to the flat plane that the rest of the solar system follows. That 15-degree tilt is not supposed to be there. Over 4.5 billion years of gravitational interaction with Jupiter and Neptune. Any orbital warp that distant should have been smoothed out long ago. The fact that it is still there today, in the data we are measuring right now, means something is actively maintaining it. Something out there in the dark is constantly stirring the pot. The Princeton team ran the simulations to figure out what kind of body would be required to keep that warp alive. And the answer they got back is the case for Planet Y. Let me break down the data, because the precision of the measurement matters. The Princeton team did not pull the 15-degree number out of thin air. Astronomers have been cataloging the orbits of trans-Neptunian objects for decades, using wide-field optical surveys from observatories on the ground in Hawaii, in Chile, and at Cerro Tololo, plus data from space-based platforms. Multiple independent catalogs have been cross-referenced to make sure no single survey is biasing the result. And the answer keeps coming back the same. The bodies between 80 and 200 AU have orbits systematically tilted 15 degrees away from the rest of the solar system. To picture what that means, think of the solar system as a giant flat plate, with the Sun at the center and the 8 known planets orbiting around it in roughly the same horizontal plane. Now picture, way out past Neptune, a second smaller plate. This second plate is not lying flat. It is rotated about 15 degrees off from the main plate. And the icy bodies that live on this second tilted plate are following its orientation. Not the main one. They are not scattered. They are not crossing through the main plane at random angles. They are organized. They are all riding the same tilted disk. This kind of organized warp, in dynamical terms, is what astronomers call a coherent inclination signal. And coherent inclination signals are extremely hard to produce by chance. The natural state of a population of orbiting bodies, after billions of years of gravitational interaction, is randomness. Orbits decay. Inclinations average out. Asymmetries get smoothed away. To still see a coherent 15-degree warp today requires an active source of disturbance. Something has to be doing work right now, otherwise the warp would have damped out hundreds of millions of years ago, and we would be looking at a flat disk like everywhere else. The Princeton team considered the alternative explanations because that is what good science requires. One possibility is that the entire outer solar system was tilted by a long-past stellar flyby, an event in which another star passed close enough to the Sun in the deep past to gravitationally disturb the outer disk. Another possibility is that the warp is being maintained by an unmodeled population of small icy bodies whose collective gravitational pull is structured in just the right way. A third possibility is that there's a single discrete object out there, embedded in the warp itself, whose gravity is strong enough to keep its neighbors locked in their tilted orbits. When the Princeton team ran the simulations on all three, the cleanest fit to the observed data was the third option. A single embedded perturbing body of a very specific mass and distance produces the warp signature that matches what we actually see. That is the planet Y hypothesis. And it does not just say there's something out there. It says exactly what kind of something. Here is what the Princeton simulations require. The perturbing body has to be in the mass range from Mercury to Earth. That gives us a span of roughly 20 to 1. Mercury is about 5.5% of Earth's mass, so the candidate range goes from a Mercury-class body up to a true Earth-mass terrestrial world. For comparison, every dwarf planet we have so far cataloged in the outer solar system, including Pluto, is dramatically smaller than this. Pluto is about 0.2% of Earth's mass, which is roughly 4% of Mercury's mass. Even the smallest plausible Planet Y candidate would be substantially more massive than every dwarf planet we know about. The body has to be in an orbit between 80 and 200 astronomical units from the Sun. To anchor that distance, Voyager 1, which has been flying outward continuously since 1977, is currently at approximately 165 AU. Light from the Sun takes about 23 hours to reach Voyager 1 at its current distance. The same light takes about 11 hours to reach the inner edge of the Planet Y candidate region, and about 28 hours to reach the outer edge. We are talking about a body that is in roughly the same neighborhood as our most distant operational spacecraft. The orbital period at 150 AU works out, by Kepler's third law, to about 1,837 years. A human lifetime would observe roughly 4% of a single orbit. The entire span of recorded human history covers approximately 4 orbits. The body has to have a moderate orbital inclination of its own that places it inside the warp it is producing. This is critical. Planet Y is not pulling on the warp from outside. It is dynamically embedded in the population of icy bodies it is shepherding. It sits in the middle of the tilt and stirs it from within. That geometry is part of what makes the inference so specific. A body in a different orbital configuration would not produce the warp at all, or would produce it in a different region of space, or would produce a tilt of a different magnitude. The fit, within the constraints of the simulation, is narrowly constrained. The Princeton team systematically searched the parameter space of every plausible perturbing body, and the cluster of solutions that match the observed data centers tightly on a Mercury-to-Earth mass rocky world embedded in the warp it produces. That is the case. That is the entire case. Whether Planet Y actually exists comes down to whether someone can independently verify it. Here is where the story gets stranger, because the very existence of a Mercury-to-Earth mass rocky body at 150 AU is a problem for our current model of how planets form. The standard model, the so-called solar nebular model, describes the planets as having coalesced out of a flat, rotating disk of gas and dust around the young sun about 4.5 billion years ago. The disk had a density profile that fell off with distance from the sun. In the inner part of the disk, where temperatures were high, water ice could not condense, and the protoplanets that formed were rocky. These became the 4 terrestrial planets. In the outer part of the disk, beyond what astronomers call the snow line, ices were stable, and the protoplanets that formed could accumulate enormous icy envelopes. These became the gas giants and ice giants, but the disk thinned out the further you went from the sun. By the time you reached 100 astronomical units, the protoplanetary disk should have been too sparse to assemble a rocky terrestrial body of significant mass. The dust grains were too far apart. The temperatures were too low to drive efficient grain growth. The dynamical timescales for assembly were too long. By every account in the current textbooks, anything bigger than a Pluto-class icy planetesimal should have been impossible to form there in situ. So if Planet Y exists at 150 AU, the obvious next question is how it got there. And the answer, no matter which way you turn it, requires us to revise something fundamental about the early history of our own solar system. The Princeton team has put 2 leading origin scenarios on the table for Planet Y. Both of them would, if confirmed, expand our model of how solar systems are built and how stable they actually are over long timescales. The first scenario is the lost sibling hypothesis. Under this scenario, Planet Y formed in the inner solar system, in the same general region where Earth, Venus, Mars, and Mercury formed, during the chaotic first 100 million years after the sun ignited. The early solar system was a violent place. There were not just 4 terrestrial planets in the early inner solar system. There were probably dozens, possibly hundreds, of Mars-sized and Mercury-sized protoplanets jostling for orbital stability. Most of them were destroyed. Some collided with each other. The collision that formed our moon, the so-called Theia impact, is one example of what those collisions actually looked like. Other early protoplanets were simply scattered out of the inner solar system entirely by close gravitational encounters with the migrating young Jupiter or the migrating young Saturn. If Planet Y is a lost sibling, that is its origin story. It would have been born in the warm inner solar system, perhaps in the same general orbital neighborhood as Earth itself. It might once have had liquid water on its surface. It might once have had an atmosphere. Then, in some violent gravitational encounter with the migrating Jupiter or Saturn during the era of giant planet migration, it was kicked out. Its original orbit was torn apart and replaced with a trajectory that flung it into the freezing outer reaches of the solar system, where it has remained for the last 4 billion years. Under this scenario, Planet Y is a frozen mirror of Earth, a terrestrial world that might have been displaced into permanent exile. The second scenario is the captured rogue hypothesis. Under this scenario, Planet Y did not form in our solar system at all. It is a rogue planet, a planetary mass body originally born around a different star, ejected from that star's solar system during some violent dynamical event, and then drifting alone through interstellar space for some unknown period of time. Recent microlensing surveys, particularly the OGL survey, have begun to reveal that rogue planets are not rare. They may be one of the most common types of object in the entire galaxy. There may be more free-floating rogue planets in the Milky Way than there are stars. If that is true, then the integrated probability that one of them, over 4.5 billion years, drifted close enough to our Sun to be gravitationally captured into a bound orbit is not negligible. Capture of a free-floating planetary body is a difficult dynamical problem, but it is not impossible, and given enough time, the expected number of capture events for any individual star is not zero. If Planet Y is a captured rogue, the implications go even further than the lost sibling scenario. It would mean that we have, embedded in our own solar system, a sample of a planet that formed somewhere else in the galaxy. We would be able to study, for the first time, an exoplanet that we did not have to view across light years of distance. We could in principle send a spacecraft to it. We could measure its surface composition directly. The body's bulk chemistry would carry the fingerprint of a different protoplanetary disk around a different host star, and we would be able to read it. Both scenarios are testable in principle. A scattered native would carry isotopic and mineral signatures consistent with the rest of the inner solar system. A captured rogue would carry signatures that look subtly different. But all of this depends on actually finding Planet Y first and characterizing its composition. We have not done either yet. The body is, for the moment, a gravitational fingerprint in the outer solar system without any direct optical confirmation. Let me give you a sense of what kind of place Planet Y, if it exists, would actually be. At 150 astronomical units from the Sun, the equilibrium temperature on the surface would be somewhere in the range of 20 to 30 Kelvin. That is roughly negative 420 degrees Fahrenheit. It is cold enough to freeze nitrogen solid. It is cold enough to freeze methane solid. Any atmosphere the planet might have once held would have long since condensed and frozen onto the surface as a thin shell of ice. There is no air. There is no wind. There is no weather. There is no liquid water anywhere on the body. The Sun, from the surface of Planet Y, is no longer a disk. It is reduced to the brightest star in a black sky. Sunlight reaching the surface is on the order of 1/20,000th of what reaches Earth. The Sun is too distant to warm anything, and too faint to cast a meaningful shadow. There is no day-night cycle in any way you would recognize from Earth. There is only a permanent dim starlight, slightly brighter when the rotation of the planet brings the Sun above the horizon, slightly dimmer when it sets. It is a place of perpetual cosmic twilight. The surface itself is expected to be dark. Bodies in the outer solar system tend to be covered in dark, carbon-rich material, processed over billions of years by exposure to cosmic radiation. The surfaces of distant Kuiper Belt objects often have reflectivity, what astronomers call albedo, of just a few percent, as dark as fresh asphalt. If Planet Y has a surface like that, it would absorb almost all of the meager sunlight that reaches it and reflect almost none back. From any practical observational standpoint, Planet Y would be one of the darkest objects in the entire solar system, intrinsically and structurally hard to see. And yet, despite all of that, the darkness, the silence, the cold, the optical invisibility, the body is massive enough to gravitationally herd the icy debris around it into a 15-degree warp that we can measure from Earth, 4 billion miles away. That is the strange thing at the center of this story. A world too dark to see is making its presence known through gravity alone. It cannot hide. The math gives it away. Every tilted orbit out there is a little gravitational note left behind, telling on it. Now, I want to address the question that is going to be on the mind of anyone who has been following outer solar system astronomy for the last decade. Why is Planet Y a separate hypothesis from Planet 9? Why did the Princeton team have to propose a new body at all? The answer is that Planet 9, in the form Brown and Badigeon originally proposed it, simply cannot account for the warp. Planet 9, in the Caltech 2016 framework, is theorized to live somewhere between 400 and 800 astronomical units from the Sun. That is 2 to 4 times farther out than the Planet Y candidate region. Voyager 1, which has been moving away from the Sun continuously for nearly 50 years, is currently at about 165 AU. To reach the inner edge of the Planet 9 candidate region, Voyager would need to keep traveling for another 70 years. To reach the outer edge, more than 150 years. That is the scale we are talking about for Planet 9. It is mind-bogglingly far away. The gravitational influence Planet 9 would exert on bodies in the inner Kuiper belt is, as a result, very weak. Yes, gravity is a long-range force. Yes, it never quite reaches zero. But the gravitational pull of a 5 Earth mass body at 500 AU on a population of objects at 150 AU is, in absolute terms, tiny. It is enough to slowly herd the perihelion points of extreme orbits over hundreds of millions of years, which is what Brown and Badigeon originally proposed Planet 9 was doing. But it is not enough to actively maintain a 15-degree inclination warp in a closer-in population of bodies. The geometry simply does not work. There's also a more technical reason that has to do with orbital resonances. The resonances Planet 9 would set up in the Kuiper belt are the wrong kind to produce the observed warp. They tend to organize orbits in eccentricity rather than in inclination. They tend to herd the perihelion points of extreme trans-Neptunian objects, which is the original Planet 9 signature, rather than tilt a population of moderate distance bodies up out of the plane. To produce the warp Princeton is studying, you need a body whose orbit is itself inclined relative to the invariable plane, sitting close enough to the affected population to exert a significant tilting torque, and massive enough to sustain that torque over billions of years against the smoothing pressure of the rest of the system. Planet 9 fails on all 3 counts. Even if Planet 9 exists exactly as Brown and Badigeon proposed, it cannot be the cause of the 80 to 200 AU tilt. That is why Planet Y is a separate hypothesis. It is built to explain a different anomaly. Planet 9, if it exists, would be a distant gas giant on a lonely outer orbit. Planet Y, if it exists, would be a rocky terrestrial world embedded in the trans-Neptunian population. Planet 9 is exotic in its remoteness. Planet Y is exotic in its proximity. And, in some ways, Planet Y is the more startling claim, because a rocky Earth-class world at 150 AU is something the standard model of planet formation says should not be there at all. I want to give you some confidence in the method the Princeton team is using, because it is going to sound on the surface like an extraordinary claim. Astronomers reasoning their way to a hidden planet they have never directly seen. But this method is not new. It has a track record. And the track record includes one of the most spectacular successes in the history of science. In the early 1800s, astronomers tracking the orbit of Uranus, discovered by William Herschel in 1781, noticed the planet did not always show up where Newton's laws predicted it should. There was a small but persistent wobble in the orbit. The French mathematician Urbain Le Verrier, working at the Paris Observatory in the 1840s, calculated that the wobble could be explained if there was an unseen planet farther out, gravitationally tugging on Uranus. He worked out, with pencil and paper, exactly where in the sky that hidden planet had to be. He sent the prediction to Johann Galle at the Berlin Observatory. On the night of September 23, 1846, Galle pointed the Berlin telescope at the calculated location. The planet was there, within 1 degree of the prediction. It was Neptune, the 8th planet of our solar system, found by mathematics rather than by accidental observation. That is the method the Princeton team is now using on the warp in the outer solar system. The bodies they can see are doing something the physics does not predict. The 15-degree tilt is the discrepancy. The Princeton team has solved for what unseen body would have to exist to produce the discrepancy. And the answer is Planet Y. Brown and Badigeon used the same method in 2016 to argue for Planet 9. The Princeton team is using it again in 2026 on a different anomaly. The next step in the method is the same step it has been since 1846. You point a telescope at the predicted region of sky and look. If the body is there, you have discovered a planet. If it is not, you have learned that the discrepancy needs a different explanation. That is where the Vera C. Rubin Observatory comes in. The Vera C. Rubin Observatory sits at an elevation of about 8,700 feet on a remote ridge in the Chilean Andes called Cerro Pachon. The site offers more than 300 clear nights per year, almost no light pollution, and one of the driest, clearest atmospheres on Earth. The observatory is named after the American astronomer Vera Rubin, who, in the 1970s and 80s, accumulated the observational evidence that established the existence of dark matter as a real component of the universe. Rubin's career was about measuring what is hiding, and the instrument bearing her name extends that tradition. The observatory achieved first light in June 2025. It entered full operations later that year, and its flagship survey, the Legacy Survey of Space and Time, abbreviated as LSST, began in early 2026. The survey is designed to run for 10 years. Over the course of that decade, Rubin will image the entire visible southern sky every few nights, returning to the same patches of sky again and again to build a cumulative time domain record of how everything in it is moving and changing. The technical specifications are extraordinary. The primary mirror is 8.5 meters across, making it one of the largest survey telescopes ever built. The imaging sensor is the largest digital camera ever constructed for astronomy, a 3,200 megapixel detector, more than 60 times the resolution of the camera in your phone, with sensitivity tuned for extremely faint objects. Each night of operation produces approximately 20 terabytes of imaging data. The total catalog over the 10-year survey is expected to exceed 60 petabytes. For the search for Planet Y, this is exactly the right instrument at exactly the right time. A body like Planet Y, drifting across the sky at a fraction of an arcsecond per night, would reveal itself in the Rubin data over weeks or months as a single pixel that systematically changes position from one image to the next. The data processing pipeline is designed to automatically flag exactly this kind of slow-motion candidate for follow-up analysis. The detection threshold is approximately magnitude 24 to 25 in red light. A Mercury-to-Earth mass body at 150 AU with a low albedo sits in the difficult middle of that envelope. If Planet Y is on the larger and brighter end of the candidate range, Rubin should pick it up readily. If it is on the smaller and darker end, the detection becomes harder, but not impossible. The survey is sensitive enough to give us a real shot at finding Planet Y within the first several years of operations. So here's where we stand. A team at Princeton has identified a 15-degree warp in a population of outer solar system bodies between 80 and 200 astronomical units from the Sun. They have run the simulations. The cleanest explanation is the existence of a hidden rocky planet, Mercury-to-Earth in mass, embedded inside the warp it produces. The candidate planet would be either a lost sibling of Earth scattered into exile by a young Jupiter, or a captured rogue planet bound to our Sun in some long-forgotten encounter from the deep past. The Vera Rubin Observatory has just opened its eyes. Over the next 10 years, it will systematically search the southern sky for exactly this kind of slow-moving distant object. By the time the survey ends, we should know. I have to flag the null hypothesis, because intellectual honesty requires it. There is a real possibility the search will turn up nothing. The warp could turn out to be a fossil from a long-past stellar flyby that no longer needs an active source. It could be maintained by a diffuse population of small bodies we have not yet detected. The Princeton simulations are an inferential argument, not a direct observation, and inferential planet claims have a mixed track record. Planet 9 has been argued for since 2016 and has not been found, and the original orbital clustering signal that motivated it has weakened somewhat as the trans-Neptunian catalog has grown. The Planet Y claim must meet the same higher bar of evidence. A clean null result from Rubin would not be a failure. It would be a discovery in its own right and would force the field to investigate the alternative explanations. But if Planet Y is real, the implications are enormous. It would mean our model of planet formation is missing something fundamental. It would mean the early solar system was even more chaotic than current models suggest, or that interstellar capture of a planet-sized body is a more common process than anyone has dared to estimate. It would mean we have been living for the entire span of human civilization in a solar system whose basic inventory we got wrong. The next decade is going to settle the question. The instrument is online. The data is starting to flow. We will be tracking this as the LSST survey progresses. And the moment any candidate detection gets confirmed by follow-up observations, you will hear about it here. The hidden world, if it is there, will not stay hidden much longer.